Hello and welcome to Systems of Equations. What exactly is a system of equation? Well, if we have something like y equals 2x plus 4, we know that that is a line when graphed. It has a bunch of billions of answers, x, y coordinates that form a line, and we get another one, 3x minus y equals a negative 1. And if we graph those two separately, down here on this graph, and we'll mark this guy in blue, so we go to a y-intercept 0, 4, and then up 2 over 1, up 2 over 1. It looks about like that. That's close enough. There we go. And the other one, let's mark that one in, say, orange. We'll do this guy in orange right here, and he's at 3x minus y equals negative 1. So that's going to be a slope of a positive 3 and 0, 1. So right here. So we go 1, 2, 3 over 1. Oh, didn't quite cross. Up 3 over 1. Oh, close. Anyway, so this guy is coming up here like this and is probably going to cross somewhere up there. Huh. All right, so there we have these two lines. And what does this mean to have a system of equations? It means that when we put these two guys together, there is going to be one guy, and you can see him right here. This guy solves the system, meaning that that xy coordinate point is the one point, x and y, that when you stick it into this line or that line, it will work for both of them. And we think, that's what a solution is of a system. So then we think, how do we find that? Well, we could take a guess. I don't know. Maybe it's over here, 3.5, 4, 5, 2. I don't know where it is. And you can get a better graph with graph paper and see where that thing will intersect. But we do have a way to do it, and it is substitution. Now let's think about substitution for a minute. With these two lines, we know how to substitute stuff in. We're like, you know what? If someone gave you the answer that, say, y equaled 5, you know what to substitute. You take that guy and you stick it right up in there and you say 3x minus 5 equals a negative 1, and then you solve it. If you were using the other guy, and you said, I don't know, let's try y equals 9. You would substitute that right up in there. And you'd say y equals 2 times 9 plus 4. So substitution means to stick in. Now notice what we have here. Y equals 5 was able to be stuck in, but if you're putting these two lines together, you can take the y equals from this line that's in orange and stick it in for the y in the other line. And then look at what happens when you do that. You don't get something that you solve here. Let's not do that guy. Let's stick that one in and we get 3x minus parentheses 2x plus 4 equals a negative 1. Holy smokes, what just happened? We now have an equation that only has one variable. These each have two variables, infinitely many solutions. Now, by substituting the one line into the other, we now have 3x, jump that in, and we get minus 2x minus 4 equals a negative 1. 3x minus 2x is x, and x minus 4, add 4 to both sides, and we get x equals a 3. What this tells us is that when we put these two lines together, this point that solves the system is 3 something. And let's see, how do we get what the other thing is? If we're on the orange line, 3 gets stuck in for x, and we get y equals 2 times 3 plus 4. Y equals, what is that? 6 plus 4 is 10. We say 3, 10. What if we were to stick 3 into the other line and substitute that guy in? Now that we know x is 3, stick it in, we would have 3 times 3 minus y equals 1, negative 1. Subtract 9 from both sides, we get minus y equals negative 10. Divide by negative 1, we get y equals 10. Yes, it doesn't matter. This 310 solves both equations. All right, let's try another one here. 3x plus y equals 5. If we were to graph this guy, 0, let me see, if x is 0, y would be a 5. That's about right there. Slope of a negative 3, down 3 over 1. Okay, so it looks, somewhat like that, off a little bit. Okay, and then the other guy, what does that guy look like? It's down here way at negative 15, somewhere down here, and then up 7 over 1, something like that. And this guy up here, keep going. I don't know, something like that. All right, so we're looking for the point that does that right there. That graph is nice, helps us to understand what's going on. Let's see how it would work with substitution. Y equals 7x minus 15. We can take this and stick it right in there and create the equation 3x plus y, which is 7x minus 15, equals 5. We now have a one variable equation. We're back in chapter 2. We know how to do this. This is 10x minus 15 equals 5. Add 15, you get 10x equals 20. That means x equals 2. All right, so if x equals 2, that gives us half of that answer. 2 what? And so now we're going to stick back in 2, I don't know where we could go right there. Let's write that guy down and see what we get. 3 times 2 plus y equals 5. That's a 6 minus 6 from both sides, and we get y equals a negative 1. So the other part of our point is a negative 1. Let's double check. 2 negative 1, does it work in both of these lines? 3 times 2 minus 1 is 5. Indeed. Y equals 7 times 2 is 14 minus 15. That's a negative 1. Yep, negative 1 equals 14 minus 15. It works. On our next example, we see, shoot, what happens if we don't have y equals something? Oh, what a great question. We know how to get y by itself. Let's take this guy over here and say, we know that y equals 9 minus 3x, or we could have written it as negative 3x plus 9. That would have been okay. And now that we have it solved for y, we can take and put it right there. What is our equation? 2x minus y, which is 9 minus 3x, equals 16. Yeah, notice that trick, that if it's not already solved for y, solve it for y. Using your magical powers from chapter 2 to be able to get y by itself, you might end up with fractions, but we can deal with those. We know how to solve equations. All right, distribute the negative, and we have 2x minus 9 plus 3x equals 16. Add those together, we get 5x minus 9 equals 16. Add 9, 5x equals 25, x equals 5. Great, we have x equals 5. Now we just need to find out the y value. Stick it back up here, either one. Let's go ahead and stick it right there. And we get 3 times 5 plus y equals 9. 3 times 5 is 15 plus y equals 9. Subtract 15 and we get y equals a negative 6. So our complete answer is x is 5, y is negative 6, and this is the coordinate, the x and the y, that solve the system, the whole thing together. Now that we've solved that particular system of equations, we want to introduce to you how to do that same thing with something truly slick called elimination. Check out this same system of equations with a little twist. We're going to, instead of do substitution, we're going to call this elimination. So it goes back early on, and we're like, with an equation, we could really add the same thing to both sides of an equation if we so chose. If you look at this, you see that if we were to add these two balanced equations together, we would get a balanced equation, but what would happen to the y's? This is amazing. See how they're opposites? If you add the equations together, first, understand you can do this. When you have two balanced equations and you add them, you'll get a balanced equation. Watch the miracle that happens here. Add these two equations together. 3x plus 2x is 5x. 9 plus 16 is 25. Y and negative y is gone. 0. Poof. Out of there. And now look what we have. Boom. We have eliminated y, so we have an equation with one single variable in it. Can you solve that? Yeah. X equals 5. And then, of course, and now just like we did before, stick that guy up in there, and we have 3 times 5 plus y equals 9. And just like we did before, y, 9 minus 15 is negative 6. And we still get 5, negative 6. Same exact thing, but look how slick that was. That was so slick, we got to do another one just like it. Let's do 2x plus 3y equals 13, and x minus y equals 4. There's going to be an XY combination here. Now, look at, I know the feeling. You want to add these right away. But if you add them, it won't eliminate a variable. Second part of the trick. So elimination has two things. Not only can you add equations together, but we still have the ability to multiply anything we want to on both sides of an equation. This plus 3y and negative y won't go away, but we could times this whole equation by 3. Look at what we just did. Can you times an equation by the same thing? Yes, as long as you do it the same thing on both sides. Now let's add them, and we end up with 2x plus 3x is 5x. 3y and negative 3y, gone. That's the purpose of elimination, is when you add them, they are gone out of the way, and these guys become 5x, and then over here we get 25. Oh, look, x equals 5 again, just like what we had up in the previous answer. Won't always happen. Caution, don't just read that into it. And then, of course, take this guy and stick it in like normal. So we have 2 times 5 plus 3y equals 13. 2 times 5 is 10. Subtract 10 from both sides and we get 3y equals 3. Y equals 1. So we now have the solution 5, 1. That's elimination. Sometimes you have to multiply and then add to eliminate a variable. Let's recap just to make sure we have the steps down. When you're using substitution, you're going to take one equation and solve for one variable. Get the x or the y by itself so you can stick that substitute, that's where it really comes in, substitute, into the other equation. Then, of course, you're going to solve that equation because you now just have one variable, one equation. Solve that, and then once you get like x equals 7, stick it back up into either equation to find its partner, y. Elimination, on the other hand, first you pick a variable to kill off, to destroy, to eliminate, which is why it's called elimination. Multiply one or both of the equations so that you have opposites on that variable. Then when you add the equations, it is gone, which leaves you just one variable. So you solve that equation just like step 3 up here. And then step number 5, stick it back in to find the partner. That is substitution elimination, and those steps will help us reference when we do our problems. To the boards! Here are some problems for you to put in your video notebook. Pause the video and then turn us back on when you're ready to see how you did. Welcome back. Hope you did all right. Let's give it a try. Here, number 1, it says use substitution. So it is requiring us to use one of those processes, which is substitution. Well, luckily, we already have y by itself. So we're going to take 2x minus 5 and stick it in for the y. So we now have 3x plus 5 times y, which is 2x minus 5, equals 27. Now look at what just happened. We now have an equation that only has one variable. We know how to do that. It falls apart before our very eyes. 10x minus 25 equals 27. So add these two together and we get 13x. Add 25 to the other side and we get a 52. Divide by 13, and we get x equals 4. I think it comes out nice as 4. We are not done yet. We still have to stick that 4 back up in. You could do it into either one of them, and you get y equals 2 times 4 now, minus 5. So 8 minus 5, y equals a 3. So that means we have the point 4, 3. Good, there's number 1. All right, number 2, let's look at that one. Use substitution. Again, it's asking us to use this particular way. This one might be easier with elimination, but alas, the instructions say otherwise. So we're going to use substitution. We've got to get y by itself with one of these. They gave us an ugly problem. Dirty, rotten scoundrels. Let's take this guy out here and solve it for y. Subtract 5x from both sides, and we get 2y equals a negative 5x plus a 7. Divide by 2, divide by 2, divide by 2, and we get y equals negative 5 halves x plus 7 halves. Oh, fractions galore. But we're going to take that and stick it in to the y right there. So we get 3x plus 7 times y, which is negative 5 halves x plus 7 halves, that has to equal a negative 19. Ew, that's just disgusting. Well, we know how to do this. Remember our 5-step process. Are there any parentheses? There are. Let's distribute. So we get 3x plus, nope, not plus, indeed. That is minus 35 halves x plus 49 halves equals a negative 19. Okay, do we have any fractions? Well, yeah, that's the whole problem here. Let's get rid of the fractions by multiplying through by the least common denominator times by 2 everywhere. And we end up with 6x minus 35x plus 49x. Yeah, I like that. Those denominators just cancel. And that equals a negative 38. All right, so combining multiple x's, 6x minus 35x is a negative 29x. And then when we subtract 49 from 38, let's write that out a little bit better. 49 and a negative 38, that's a negative 87. All right, negative 87. I hope this comes out nice. Divide by a negative 29, divide by a negative 29. And we get x equals positive 3. Wow. Are we done yet? No, we got to find the other half of the point. We just found the x coordinate of those two. So let's come over here and stick it in. I don't know. We could go either one of them. But 5 times 3 plus 2y equals 7. 15. Subtract 15 over there, and we get 2y equals a negative 8 by subtracting 15. And then y equals a negative 4. So we get 3 comma negative 4. Does that really work in both of them? 5 times 3, 15, plus a negative 8, indeed equals 7. 3 times 3 is 9, plus a negative 28 equals 19. This is the one and only point that works in both equations. So yes, indeed. All right, let's see if this one is any nicer. Solve. Oh, look at that. Just solve. That means we could use elimination or substitution. And oh, this is set up beautifully for elimination. If we add these two together, the y's will go away and we'll have an equation with just one variable. So let's do it. Add these two together. I'm going to put it like this. You could add them straight down. 2x plus 7x is 9x. 17 and 1, that's 18. So we get 9x equals 18. X equals 2. Oh, good. Now let's stick 2 back up in here. We get 7 times 2 is 14 plus y equals 1. That is subtract 14 from both sides, and we get y equals a negative 13. So the point is 2, negative 13. And that is the only point that works in both of those equations. All right, number 4. Solve this. Ooh, we can use substitution, which will get us these kind of bad fractions, or we can use elimination. I vote elimination. Let's try it. The y's we'd have to multiply by 8s and 5s. These we'd have to multiply by 2s and 3s to get them both 6s. I'm going to do that. Let's take these guys right here, times this guy by a negative 3, and this guy by a 2. Will that work? Let's write it out here just to make sure that's all right. Negative 6x minus 15y equals negative 27. And this one is 6x plus 16y equals 26. Huh, look at that. Okay, so if we add them, negative 3 times 2 and 2 times 3, that gives us 6 and negative 6. The x's are gone when we add them together. Negative 15 plus 16 is 1y equals, and then negative 27 plus 26 is a negative 1. So y is negative 1. Hey, look at that. So now let's stick it in and write 2 times x plus 5 times a negative 1, which is negative 5, is going to equal a 9. 2x, this is negative 5, add it over and we get 14, and x is 7. So we get the point 7, negative 1. Does that really work in the other guy? 3 times 7 is 21, plus 8 times a negative 1. 3 times 7 is 21, minus 8 is indeed 13. Good. Here's one of the most interesting uses, or maybe abuses, of systems of equations is being able to turn decimals into fractions. Now, we know that any decimal that stops or repeats is actually a rational number, which means it can be written as a fraction. It's easy when it stops, like 0.5. What is that? Well, that's 5 in the tenths place, so that's easy to write, 5 tenths, and then we reduce the fraction and we get 1/2. Same thing with everything that stops. But what about when it repeats, like a 0.3 repeater, goes on and on forever like that? Well, we know that's going to be 1/3, but how can you turn it into that if you didn't know that? And it turns out that this system of equations thing turns out to be very valuable. If we know this number x is 0.333 on forever, we can actually manipulate this to create another equation that will help us. For example, times by 10. So 10x. Well, when you times by 10, the decimal goes over. And do we still have the same number of threes? Yep, they go on forever. Now this is we only have one variable, but we've set up kind of a system of equations that will help us get rid of the decimals. If we subtract these two equations, 10x minus x is 9x, and 3.33333 minus the 0.33333 that we had before, we now have 3. Can we solve this? Indeed, x equals 3/9, or 1/3. And we've changed that decimal, which was x, to 1/3. Let's try another one that's not so easy. What if about x equals 0.4545 forever and ever like that? Well, in this case, in order to use a second equation to cancel all those out, we'd have to times by 100. So we take 100x, and that equals 45.45 on forever. Like that. Yes. So now when we subtract them, we get 99x equals, and then that guy goes away with that one. It's gone completely. They go on forever and ever. So we now have 45 right there. So the idea of adding, subtracting equations, even though we only have one variable, that's what I kind of meant. It's an abuse of the systems of equations. Usually systems of equations solve for two variables, but here we're using it to write this number in a couple of different ways that will allow us to cancel out the fractional portion. So divide by 99, divide by 99, and does that guy simplify? Take out a 9, take out a 9, and we get 5/11. And you can try it if you took 5 divided by 11. Oh, yeah, 11 goes into 5. Nope, 11 goes into 50 4 times, and you get 44. Subtract, and we get 60. 11 goes into 65 times. 5 times 11 is 55. Subtract them, and we're right back to the 50. So it will repeat 4545 forever and ever. Fascinating that we can use those systems of equations to go back. Okay, now back to your regularly scheduled instruction. Before we move on to the big 3 variables and 3 equations section of this systems of equations, we need to see what happens if. There are some unusual special things that might occur here, and so I wanted to show you what might happen sometimes. So let's take a couple of lines like y equals 2x minus 3 and y equals 2x plus 4, and let's solve this system of equations. Here, this one looks like it would be prime for substitution, where we already have one variable solved for, and we stick that guy in right there, and we now have 2x minus 3 equals 2x plus 4. Try to get the x's together, and you might remember something like this happening from chapter 2, where we have negative 3 equals 4. And even if you added 3 to both sides, you'd still get 0 equals 7, both of which are, ooh, that's a clear indication of no solution. And if we look up here, we can kind of see what happened. This is y equals 2x minus 3. That's 0, negative 3, and then a slope of up 2 over 1. So it kind of looks like that. And then y equals 2x plus 4. That's up at positive 4, up 2 over 1. And you'll notice that these guys, they have the same slope. We learned that that was parallel lines. They're parallel, which means they never cross. Yes, when you solve these equations, the answer you get down here tells you when crossing happens, when intersection happens. And this intersection happens when negative 3 equals 4, when 0 equals 7, which is never. There is no solution to this system of equations. Let's look at one more. Here's a system where we're looking at this, and it looks like it's going to set up pretty nice for elimination. You pick a variable and you're like, I would like to get rid of the x's. So we're going to take and times the top guy by a -2. Let's write it like this and see what's there. We get a -4x. Good, these x's will cancel. Minus 14y equals a +10. Now add these two equations together. -4x plus 4x is 0. -14y plus 14y, that's 0. They both went away at the same time, equals 10 and a -10, that's a 0. Oh, back in the day in chapter 2, this thing we got and we said, oh, all real numbers. That's not technically the case here because it's not all x and y combinations, but it does give us the clue that there are infinite solutions. In particular, infinite solutions, write that out. Remember, this tells us when these are intersecting. And that means that these two lines, if you were to graph them, they turn out to be intersecting all the time. Always intersecting, which means we have an entire line of solutions. We don't need to write down what the solutions are because they're right here. It's all of those xy coordinate points. The billions of answers to that line will work in the other one. Infinite solutions. So those are our special cases. Let's put that right over here as kind of a little insert. And now we are here in 3 variables. Notice when we have 3 variables, such as an x and a y and a z, the system has to include 3 equations. So this is the same number of equations as variables, and you have enough information to find them. Now, we're going to be using both what we learned in substitution and elimination. We really don't know what we're doing with 3 variables, but if we can use substitution or elimination to knock it down so that we can eventually solve an equation with 1 variable, then we got it. So let's look and see how this works with substitution. First, some of them will be set up like this, where look at y is in terms of x, z is in terms of x, and we're able to take, that y goes right down there, and the z absolutely goes right in there, and you can substitute those in, and look what we have created, 5x plus 2, but notice now the y, once we stick it in, is 2x minus 3, and the z is, we're going to subtract the z, which is a -3x plus 4, and that is all going to equal 14. So we stuck those in, stuck the y in right there, 2x minus 3, stuck the z in right there. Make sure you got that in parentheses, so if you have to distribute anything, you can. And let's solve it. Look at, oh, happy face. We have an equation with 1 variable in it. So we now have 5x plus, that'll jump in, 4x minus 6, that jumps in, and we get minus, nope, that's a plus 3x minus 4 equals 14. So 5x and 4x and 3x is 12x minus 10 equals 14. Add 10, we get 12x equals 24, x equals 2. Now notice what happens when we get x equals 2. Once we've solved it, exactly what we were doing before, stick it back in. So when we stick it back in up here, we get y is going to be 2 times 2 minus 3. That's going to be 4 minus 3 is a -1. And -3 times 2 plus a 4, that's -6, plus 4 is a -2. So x is 2, y is -1, and z is -2. 2, -1, -2. Excellent. And now we go through one where elimination is most valuable. And notice we pick a variable to eliminate. If you look at this, ugly looking problem, we've got x's and y's and z's. We're going to have to eliminate a variable. Now remember, we're going to get down and add the equations and eliminate a variable. And we're going to do that twice. So we've got to pick a variable to eliminate twice. So when we look at this thing, x's and y's and z's, it looks like the z's are set up pretty nice. Look, we could eliminate z's by adding those. We'll have to times by something there. The y's, that's kind of close. Not bad, not bad. Looks like the z's will be the easiest. You get to pick which variable you want. So to start this off, we're going to take this equation, this system, and we're going to move it right down in the middle. Give us lots of room to work with, and then do this piece at a time. So we're going to pick z, and let's write that up here at the very beginning. Pick z. So we've got to get him twice. Gone. So if we take these two and these two equations just exactly the way they are, 2x minus y plus z equals 11, and 3x plus 2y minus z equals 8, and add these two together, we get rid of z. 2x plus 3x is 5x. Negative y plus 2y is plus y. Plus z minus z, they're gone. That's why we did it. And then 11 plus 8 is 19. Excellent. And then we've got to get rid of the z again. So now we're going to do it another way. So let me see. If we took and times this top guy by 2, we'd get a positive 2z to go with that negative 2z. So let's do that. Let's do this one. We're going to times by 2 here. Notice we could use any of these. So we're using the top equation twice, just going back to the beginning. That's perfectly fine. So 4x minus 2y plus 2z equals 22. And then the bottom one comes straight across right here. We could times it by something if we needed to, if you ever find yourself in that situation. So we get x minus 4y minus 2z equals 4. And when we add these two together, 4x plus x, that's a 5x, minus 2y minus 6y, no, minus 2, yeah, minus 6y equals 22 plus 24 is 26. Excellent. Now notice what we have here. We now have two equations with two variables. That's exactly what we've done. We've reduced it down to two variables, two equations, and we know how to do this. So if we put these two together, and let me see, we're going to try to eliminate between this equation, let's change our color, between this equation and this equation, let's see. Oh, if we times like this guy by a negative 1, it becomes negative 5x plus 6y equals a negative 26, and we leave this guy just normal at 5x. Let's say we're going to bring him right down here into the middle. 5x plus y equals 19. See how we did it so that the 5x and the negative 5x would eliminate? Indeed. Negative 5x is gone. 7y equals negative 7. Divide by 7, we get y equals a negative 1. So notice how that worked. We were up here with three variables, three equations. By taking two of them at a time, eliminating one variable, we now have two equations to go down to this next step where it's a two variable, two equation problem, which then we eliminate one of the variables and we're now down to one variable, one problem. So then we just kind of walk back up. So with y equal to negative 1, let's go right back up in here and say now we have 5x minus 6 times a negative 1 equals 26. That's 5x plus 26. Oops, not 5x plus 26. 5x plus 6 equals 26. Subtract 6 from both sides. 5x equals 20. And then divide by 5 and we get x equals 4. So now we have the x and the y, and we can stick it back up into one of the original equations to find z. So let's go ahead and use this top guy here. And notice what we can write down now. We have two x's. We just stuck this one right up in there. And then the y is negative 1. So we're going to put him right there. Minus a minus 1 plus z equals 11. That's 8 plus 1 is 9 plus z equals 11. Subtract 9 and we get z equals 2. So the end results, the end answers are x is 4, y is negative 1, z is 2. Excellent. These are huge problems. Start right in the center and get rid of a variable on one side, get rid of a variable on the other side, bring them together in the middle, eliminate another variable, and that's elimination. To the boards! And to finish up, let's make sure you guys get the opportunity one more time at the boards. Pause the video, write down these problems, put them in your notebook, and then resume when you have given it a shot and need to check to see how you did. And welcome back. All right, here we go. Whoa, this has got 3 equations and 3 variables. That's good. But notice that these are already solved for the x's. So actually this one will be valuable with substitution. So 2x minus 7 goes in for y, and x plus 2 can go in for z. So we actually have x plus 2 times 2x minus 7 minus 3 times x plus 2 equals a negative 16. Substitution, especially in word problems, will come in handy. So don't forget that you can substitute, and that'll work. We'll use elimination down here, but this one was set up for substitution. So x plus, get the fractions done. You get 4x minus 14 minus 3x minus 6 equals a negative 16. How many x's? X and 4x and minus 3x, so that'll give us a 2x. Minus 14 minus 16 is a minus 20 equals a negative 16. So add 20 to both sides and you get 2x equals 4. X equals 2. We're not done. We got to stick that back up in there. So what does that mean? We have y equals 2 times 2 minus 7 equals 4 minus 7 is a negative 3. And z equals x is 2. So we have 2 plus 2 is 4. So we have 2, negative 3 is y, and 4 is z. So that is our point of intersection of these 3 equations. Good. Now let's move on down to this guy right here. First, move it off to the center. You can see we've kind of done that. And then let's pick a variable to eliminate twice. Z's would be very easy. Y's also, there's an easy one here. Let's go ahead and take care of the y's. So if we just take this guy and put them over here with 2x minus y plus z equals 12. And x plus y plus z equals 5. And add those two together, we get 3x, y's are gone, plus 2z equals 17. All right, let's try another way. Let me see, another way to eliminate the y's. If we times the top guy by 2, it'll make it cancel with the bottom one. So let's do this, times this guy by 2, and just leave this guy out just normal. So we end up with 2x minus, I just didn't times it by 2 there. 4x minus 2y plus 2z equals 24. And then the next one, this is a 3x plus 2y minus z equals 12. We left him all alone. And the y's cancel. 3x plus 4x is 7x. 7x, y's are gone, plus a z equals 36. Marvelous. Now, if we look at what we have left, we're trying to get rid of the z's. So when we bring them together, let's see if we can bring them together. This guy can come down just straight normal. So we get a 3x plus 2z equals 17. And this guy, if we times him by 2, then, a negative 2, then those z's will cancel. So times by negative 2, we get a negative 14x minus 2z equals a negative 72. Add those together, and we end up with negative 11x. Z's are gone equals 17 minus 72, that's a negative 55. Divide both sides by 11 and we get x equals a positive 5. Now let's notice there's kind of our first step, and then we get the second step with just 2 equations with 2 variables. So let's go ahead and stick this back in, change color just a little bit so we can identify our solutions here. Stick x equals 5 back into one of these two equations. How about this guy right up here, right there? So we get 3 times 5 is 15 plus 2z equals 17. Subtract 15 from both sides, 2z equals 2, and divide by 2z equals a positive 1. Then we take that and put it back up here into the very top one. Any of those, let's try this guy right there, and we'll highlight him and write him down over on this bottom left side. We have x, that's a 5, plus a y, we don't know what it is, plus a z, which is a 1, has to equal a 5. So we've taken this guy right here and stuck in the x and the z. So subtract 5, 5 plus 1 is 6, subtract 6, and we get y equals a negative 1. So that gives us a final answer of 5 for x, negative 1 for y, and 1 for z. We should note that if you chose to get rid of the z's, you'll have a different second step and a different third step down here, but you will end up with 5, negative 1, 1. Great. All right, let's look at number 3. Here, number 3 and number 4, we put in here to make sure you had some practice with no solution, all real number. Let's see if you got it right. So in elimination, do you want to get rid of the x's or the y's? Let's get rid of the x's. We'd have to times the top guy by a negative 2. So negative 4 plus 4 is 0 x's. Okay, good. The y's, negative 6y plus 6y is 0y, so we get 0 equals negative 16 plus 8 is a negative 8. 0 equals negative 8. You should feel very weird having written that, and yes, indeed, that is a no solution. That will never happen. These two are actually parallel lines that go through different intercepts, so they will never cross. That means there is no x and y coordinate that will work in both of them. All right, number 4. Let's do it again. Let's times the top guy by negative 2. It's almost the same as the system up there. We get negative 4 plus 4 is 0. Negative 6 plus 6y is 0. So we get 0 equals negative 16 plus 16 equals 0. This one is true, and it's always true, which means that these two lines are always crossing, which means you have an infinite number of solutions. In later math classes, you will be able to write down what those solutions look like. It might be the line here in this case, or if you have a three-dimensional one, it might be a line or it might be a whole plane. But right now we'll just settle for infinite number of solutions. Infinite number of solutions. Good. And there you go. Good luck with the homework.